To continue on with 2D interference, we've mentioned a number of times that yes, when you have two sources you get this weird pattern, and we simplify it into this, and we have nodal lines, and in the last example I drew two nodal lines. There can be lots and lots of nodal lines. It depends on the arrangement of how far the two sources are and what the frequency is. So in this case I've got three nodal lines. Up the middle here I've drawn the central maximum. Now in the last video we defined the distance x to my point P. I pick a point on a nodal line, and there's some underlying mathematical formula that governs this. And we had the first formula is PS2 minus PS1 equals n minus half lambda. Then we said, well, we could define this point P and say there's this distance x here from the central maximum and this distance L here. And we came up with this formula. We said that this formula includes our new variables x and L and the distance between the two sources. Well, if you look at this triangle created here and you look at this angle, there's an angle from here to the nodal line. Now I know the nodal lines are curved, so it's a bit of an approximation. But even this formula is a bit of an approximation. It really only works well when the distance L is fairly large and x is fairly small. So for our geometry, I didn't derive the equation, but for the geometry we have, you have to recognize this is a bit of an approximation. The formula PS2 minus PS1 equals n minus half lambda is accurate. So if I look at this, I draw a line along the nodal line to sort of approximate what's going on, and I can come up with an angle. And as I said, as this gets further away, it becomes a little simpler to see. So this angle here, well, we know the sine of an angle is the opposite over the hypotenuse. So using those same variables, I can say the sine of the angle to the nodal line is equal to x over L. And that appears in this formula. So what I can do is I can take sine theta and plug it in here instead of x over L, because x over L is sine theta. When we do that, we don't write the formula as lambda equals sine theta times d over n minus a half. We rearrange the formula, and we end up with a formula like this. Sine theta equals n minus a half lambda over d. And again, because this formula is based on this formula, it is a good approximation as this point gets further away. So I've now got a third formula for this pattern. And this formula has a different variable. It has the angle in it. So I'm not going to do a sample problem because basically I give you a bunch of numbers and you plug them in there, and I'm either looking for the angle, what's the angle to the second nodal line, or I'm going to say what nodal line is that point on, or what's the wavelength, or what's the distance between the two sources for this pattern. Now if you look at the numbers I used for the last example, it may not work with this formula because when I made those numbers up I didn't take into account everything I needed to. So you can make up your own sample problem. What we're going to do with this now is we're going to come up with another formula for this type of pattern that works well with an experiment called Young's double-slit experiment, where we can use two sources very close together, create a pattern in light, and end up calculating the wavelength of light. So that's what we'll be doing next.